Okay, here we are. Welcome back. Happy Friday. Today is our 11th class of the semester. We're moving on to chapter 2. Today is the basics of functions and their graphs. Next class, more on functions and their graphs. In fact, one more of these, more on functions and their graphs. Next 3 classes after that, transformations of functions, linear regression, and then combining functions, inverse functions, and then our test. What word do you see? Functions. Functions. A big part of this class is about functions. So I'm assuming that many of us have heard of functions before, and many of us might already be quite comfortable with them, but it's totally okay if you've never seen that word in a math context before. We're going to introduce it today, but you can see that functions are the central theme tying together all the material between now and the second test, okay? All right, just looking on the horizon, project 2 is going to be assigned. I haven't given it to you yet. But it looks like on Friday, a week from today, I'll hand you project 2. You'll hand it back to me October 24. Someplace in there is a quiz. So nothing on the immediate horizon. There's nothing outstanding other than the regular homework day to day. Questions? Okay. So the preview exercises we're moving past, and we're going to come down here to page 2 with our demo. All right, so first definition here is about something called relations. We're going to start with number 1. Suppose we select David Lee, Avery Bradley, Jared Sullinger, and Isaiah Thomas from the 2015-2016 Boston Celtics team roster and listed their heights, 6'9", 6'2", 6'9", and 5'9", respectively. All right, 4 basketball players and their heights. So we can write this correspondence between names and heights using a set of ordered pairs. So I'm just going to highlight one thing here. There's David Lee. He is 6'9". That's an ordered pair, just like an X and a Y. It's a little bit weird in that the X is not a number, right? It's a person. It's a name. That's okay. And then there's a comma after that whole thing in parentheses, and that's how we list things inside of a set using this this roster notation. And so there's a set of 4 things all in parentheses. Fair? Okay, the set of ordered pairs above is called a relation in mathematics. A relation is any set of ordered pairs. All we're doing is relating the person to their height relation. Number 2, the set of names, the 4 of them are listed there, is the set of all first components, which are the inputs, of the ordered pairs, and is called the domain of the relation. So domain is a mathy word that probably you have seen before. Domain is always the set of inputs that we're talking about. In this case, it's the 4 people. The set of heights, 6'9", 6'2", 5'9", is the set of second components, outputs, and it is called the range of the relation. So domain is always inputs, and range is always outputs. What do you notice about this collection of heights compared to the original list? There's 1 less. How come? Yeah, there's 2 6'9". So when you're listing things in a set, you don't need to list repeats. So there's just 3 things in the range there. That's fine. Okay, so we've got domains and we've got ranges. Just to help us keep them straight, we have input and output. And which one is y? If we have an x and a y, which one is which? Y is the output, right? And so that means x is the input, the thing you put in. And then we've also got 2 new words, domain and range. Which one is domain? Domain is this first guy here, right? The input or the x, and the range is over there. And the one nice thing about each row in that table is that it's alphabetical. Alphabetically, input comes before output, yes. Alphabetically, x comes before y, yes. Alphabetically, domain comes before range. So even if there's new vocabulary, we've got this neat little mnemonic. It's all alphabetical. Okay. So moving down here, we've got this picture. We've got the domain for first names only, and then we've got the range over there with just the 3 of them. And then we've got the arrows. And so just looking at the arrows, you can tell exactly how tall each of these folks is, right? So for example, Isaiah is how tall? 5'9", and that's just representing that ordered pair that we saw up above, Isaiah, comma, 5'9". And you'll notice that, yeah, even though we have only 3 entries on the right-hand side, how do we accommodate the duplicated one? Is that 2 arrows going into 6'9", right? So that is just a graphical way to represent exactly the same list up above. Okay. We could just as well write all of that information, but in reverse. Put the heights first, and then put the names second. So 6'9" David Lee, 6'2" Avery Bradley, same exact stuff, but just reversed. In the previous example, which one was the domains, the heights or the names? The names up there were the domains. What are the domains here? Is the heights is the domains, right? So they just swapped domain and range. Okay, so let's see if we could fill in this relation right here. All right, so domain, I've got 6'9" and 6'2" and 5'9", and that's it. We only had 3 of them because of that duplicate. Okay, and then we'll go ahead and list the names here. I'm going to put them in backwards order just to change it up a little bit. So I'm going to put Jared first, and then Isaiah, Avery, and David. Once you've got all that information in there, go ahead and draw some arrows in. Make sure you match people with the correct, match the heights correctly with the names. And so I've got my collection of 4 arrows. Everybody okay? All right, and then in number 4, it says, suppose that the MVP, most valuable player for the season or for the team, goes to the player that's 6'9". Is that enough information for you to determine who gets the award? No, because 2 people that are 6'9". Okay, so hopefully we can kind of see where we're going with this. I mean, we're going to get rid of these names in a minute and just talk. It's all going to be numbers for us, right? X's and Y's are all going to be numbers. But there's something funky going on here in that in this picture, 6'9", the single input of 6'9" has 2 different outputs, right? And that leads to a problem in this scenario where we can't tell yet who gets the MVP award. All right, next page is our introduction to functions. We used the word relation. Any collection of ordered pairs is a relation. We saw 2 of them. The first one, we had the names and then the heights. That's a relation. Then we swapped them, heights and then names. That's also a relation. But functions are more restricted than that. So here it goes. Previous example shows us that knowing the basketball player's height did not help us determine which player to give the trophy to. This is an example of a relation that is not well defined. Not well defined. Our work in this course will mainly focus on well-defined relations. A well-defined relation, also known as a function, there's the first time we're seeing this word, has exactly 1 output value for any input value. To pick an input, there will be 1 and only 1 output. That was not the case with the picture at the bottom of that previous page. 6'9" was a single input, but how many outputs did it go with? 2. And so that picture at the bottom of the page was not a function. So here's number 5. It says the first example that we did was where the names were first and the heights were second, and then below it's the heights first and the names second. It says which ones, let me do this guy first. Which sets represent a relation? Remember, a relation is any collection of ordered pairs. H is a relation. What about P? A relation could care less about whether or not it's a function. A relation is any set of ordered pairs. So P is a relation. Both of these guys are relations, okay? So which sets represent a relation? Both. Any set of ordered pairs, you don't even have to look and see where the arrows are going. But for function, you got to be more careful. So it says which sets represent a function. To be a function, single input can only have a single output. Which one of these guys is not a function? H is not a function because for H, we have 6'9" going to both David Lee and Jared Sullinger. That is not a function. That is the key defining characteristic of what it means to be not a function. A single input is going to two different outputs, not a function. But in the first row, we don't see that. In fact, there's no chance that the first row isn't a function. How come? What made it go wrong in H? There was two what? There were two outputs for the single 6, 9. 6, 9 appeared twice in the input spot, right? That was the problem. But what are the inputs in P? David, Avery, Isaiah, and Jared. I don't even need to look at the Y values. That's a function. Because it never has any chance to have this issue where you have 6, 9 going to something and 6, 9 again going to something else. I see 4 different inputs in this first row, 4 names. That's a function. Doesn't matter what the second things are. I'm not at all bothered by the fact that I see 2, 6, 9s there. It's no problem that we got a couple of Y's duplicated, a couple of outputs duplicated. So which set represents a function? That is P and P only, okay? Okay, next thing here, really, really important once we got this function relation distinction behind us, is function notation. Number 6, the table below lists the height of a baseball, Y, in feet at various times X in seconds. So the top row is the height of a ball, the bottom row is how many seconds that ball has been in the air. To be honest, I would prefer that the table have the rows swapped. I prefer my what do I prefer? I prefer my inputs, X's to be in the top row, and my outputs, Y's to be in the bottom row. Okay, it says the values listed above represent or define a function. We say that Y is a function of X. So how do I know that? Take a look at these X's. They're all getting mapped to some number in the top row. Do you see any X's that are duplicated? No. So it is automatically a function without even looking at the outputs. Don't even need to look at the heights. I don't care about those numbers. The only way for something to fail to be a function is if 2 copies of the same input end up going to different outputs. And we don't have that here. And so we say Y is a function of X. Y is a function of X. Typically, those are going to be that's going to be the order for us. Y is going to be a function of X. I don't really have a great mnemonic thing here, but Y is something with X. It kind of reminds me of the word yikes. I used to watch Scooby-Doo when I was younger. So that's like our normal order. Y is a function of X is this thing. Okay, so brand new notation. We're just going to jump down and do a specific example here. Number 7. This thing down here, F parentheses 2. Raise your hand if you've seen it before. Function notation, F parentheses 2. Raise your hand if you've never seen that F parentheses 2 thing before. Totally okay if you never have. I think we're actually about 50-50 here. So just be patient with yourself. Some people have a ton of experience with this F parentheses 2 business. For some people, it's brand new. We'll get good at it. Just got to be practice. Just have to practice. Okay, F parentheses 2. First of all, it looks like multiplication. It isn't. It looks like F times 2. It's not. It is F of 2. It's written right up there. Parentheses for the first time don't mean multiplication. Of. F of 2 is what we're after. So here's what we're going to do. We are going to look at this table. I'm going to tell you that the function is almost always the Y value. So I'm just going to say that the F is that first row, and we can keep X as the second row. So F of 2 means that you look in the X row, and you're looking for the number 2. And in this case, we see the number 2 right here. And F of 2 is the Y value. F of 2 equals 99. Put that in the blank. 99. F of 2 equals 99. See if you can use the table to fill in the next blank. F of 0 equals something. So again, that 0 is an X. You look in the table, you find 0 for X, and what do you get for the Y? 3. Part C, a little bit trickier. It says f of x is 103, and I'm looking for an x in this case. And that 103 is the y. So you're going to look for 103 is not in the x row, but in the y row. And where do you see that 103 in the y row? X equals what? 2.5. Anyplace else? No. Okay, so x equals 2.5 gets us to 103. Good. All right. So here's some translations that I want us to start thinking about here. The guy in the parentheses, is x. And in case it's a different letter, it's the input. The guy in the parentheses is the input. In parentheses, input. Almost sounds the same, right? In parentheses, input. The guy by itself after the equal sign is y, or more generally, the output. Okay, input in the parentheses, output is the thing by itself after the equals, all right? There's really only a couple of ways to mess this up. One, you can accidentally swap the roles of these two things. With a little bit of practice, hopefully we won't do that anymore. The other thing we can do is just think that parentheses means multiplication, because for many years, until you are first introduced to functions, that's the only thing parentheses is. It's just a way to separate, and it often means multiplication, but that's not this. This is a brand new notation. Unfortunately, it overlaps with parentheses that you have a lot of experience with, meaning multiplication, okay? Each of these things has a sentence. We're not going to write the sentences here, but for example, this 2 is 2 what? Feet or seconds? That is 2 seconds. It's the input. 2 seconds into this experiment, the ball is 99 feet in the air. 0 seconds into this experiment, the ball is 3 feet in the air. Said another way, at the start of this experiment, the ball is 3 feet in the air. If I want to know when the ball is 103 feet in the air, the answer is 2.5 seconds in. Okay? All right, so I think that is good. Activities start right there on the next page. Again, take your time, especially if this is brand new to you.